All right, these dimensional analysis quizzes, I will have them graded and you will be able to see them before you take your test. I usually do it the day before the test and you can look and see exactly how they got graded so that you know what to improve for the next time. So those will be coming. And then what are we all going to make sure that we have tomorrow in class? Closed-toed shoes. Guys, I'm getting ready. I got them all printed out, right, sorted, ready to go to do our paper towel lab. So please make sure you get to participate by having your closed-toed shoes. Wherever you need to make a reminder, take a second right now and do that quickly. If that involves a phone, get it out, make your reminder, and then put it away. Okay. All right. So with that, let's check out percent error. Guys, it's about the steps. That was the main thing about getting full credit here, is you had to break it down into steps. Okay, you had to separate out all of the subtractions and the divisions and multiplications. Okay, so let me start here with number 2. I'm going to be up front. Guys, I hate number 2. I hate the scientific notation. So let me show you what I did here. In this part, I left everything in scientific notation. I never took a single number out of scientific notation, meaning I had 2 decimal places and 2 decimal places right throughout. However, since the exponents were different in scientific notation, they technically are not the same number of decimal places. So what I did down here in purple is doing it where I actually took them out of scientific notation and followed my rules. It did make a difference in the significant figures of your final answer, whether it was 24.2 if you left everything in scientific notation or 24 if you took everything out. I'm not going to put that one on your binder quiz. If you wrote either 24 or 24.2, that's going to be correct here, and you would not encounter one like that on your test. I'm not going to make it that confusing. Probably it's better to take it out of scientific notation. Just FYI. All right, so other than that, do we have questions on 1 through 3? And again, it's about the sig figs, so it's not just close to 5. It needs to be exactly 5 to be the correct answer with sig figs. Yes?
Do you always type that extra math number in your calculator?
Yes, that's why it's there. The math number needs to be there only for the calculator.
Oh, okay.
Right? That's the main purpose that it's there. So we didn't have any extra numbers on 1 through 3. It actually worked out nicely that there was no math number that we needed to have, because what I marked in every calculation, which was really just this one, that's the only one that we would have kept an extra digit with. They all came out to be where they needed to be. Okay. All right, other questions 1 through 3? Units, make sure we're putting units on everything. The units don't cancel out until right there. Also, I saw some very strange units on final answers. You're calculating a percent. Your unit should be the percent sign. Nothing else. All right, so now we get to the bottom part where we had to split it up into the 4. So in my pink, that's my adding. No extra math digit was needed in either case because it came out to have the correct number of decimal places with no extra digits. There's my averaging, dividing by 3 to get my average. I saw some students dividing by the accepted value here. Nope, you're just averaging, divide by 3. In each of these cases, we did have a math digit because they did not come out to be the exact number of sig figs, right? There were numbers after where we would have had our last sig fig. So in this example, number 3, that's just a math number. And also here, number 3, that's just a math number. Okay, there for math purposes only. So then we move on to our error calculation. This is where you guys would probably have some struggles on making sure you have rounded it the right way. If this is my math number, that means that is only a 1 decimal place number as far as sig figs is concerned. So we had a 1 decimal place minus a 1 decimal place. That would give me a 1 decimal place, but again, there were extra digits. So I marked the first decimal place, kept the extra digit. Same thing down here. That 3 does not count as a decimal place. It's just the calculator math number. So that was only a 1 decimal place number. But then each of these had another math digit. All right, and then so we finished up with the percentage, and now it's sig figs. Guys, when I marked that first 7, that meant only the 1 and the first 7 were sig figs. There's only 2 sig figs there, the 1 and the first 7. The last 7 is just a math number. Right? And then down here, the 0.43, the 4 that's marked, that's the only sig fig. The 3 is not a sig fig. So that's why 2 and 1 sig fig respectively were these answers. Mrs. Tate, down here, it looks like you did the accepted minus the experimental instead of the experimental minus the accepted, right? Guys, I'm going to be honest. I mix those up all the time. Like the equation, it's honestly, in the end, not that important, because what do we do in the very next step with our answer? We absolute value. So whether I do 10 minus 8 or 8 minus 2, right? Negative 2 and 2, the absolute value is still going to be 2 for both of them. So it ultimately doesn't matter what order you subtract them in. In fact, there are times when I just always do the bigger number minus the smaller number to make sure I always get a positive answer, right? So don't let that hang you up about that order. Okay. So questions right now, 4 and 5. All right. Then with that, guys, we are almost wrapped up with our unit, right? We got a test next Wednesday. So right now we need a blank sheet of paper for number 15, graphing/psi method notes. You also have your graphing worksheet that's number 16, but this is number 15. We're just going to hit on a couple of things that the graphing worksheet doesn't cover, right? So guys, graphs, we're still talking about data. We talked about accuracy and precision, how we can describe the quality of our data. When we talk about graphing, that's about the analysis of our data. And what better way to analyze and figure out what kinds of information we can get from our experiments than by making pictures. Guys, that's what a graph is. It's a picture. It is a picture of data. Looking at a whole bunch of numbers in a table, man, that's hard sometimes. So actually to see what's actually going on, what the relationships are, what the patterns are, that's where graphing comes in. So there are 3 main types of graphs that you would see. Okay, guys, if we could put away our worksheet for a minute and come here to our notes, that would be great. All right, we have a circle graph, we have a bar graph, and we have a line graph. Circle graph, bar graph, line graph. Those are the 3 main types of graphs. Now, what we need to understand is why one graph would be more appropriate to use versus another in a particular experiment, right? So it depends on what the emphasis is on what you're trying to convey to eventually the reader of whatever lab report or journal article that you're writing. When we talk about circle graphs are always about parts of a whole. So when I was in middle school, our teacher had us practice making circle graphs where we had to track everything we did all day, how much time we spent, and then we had to make a circle graph where the whole was the day, the 24 hours, and then each of the slices of the pie was how much time we spent doing different things. It was a percentage of the day. Yeah. So that would be an example of a circle graph, right? I want to know, hey, in my day, what's the biggest wedge, right? If I'm talking about a bar graph, bar graphs are best at just showing comparisons. It's really easy a lot of times to see, hey, this bar is tall, this bar is short, these bars are about the same, right? You just want to know big or smaller, generally in a bar graph. That's going to be your emphasis. So in a bar graph, it could be, I did a survey of Plant High School students, and I want to know what their favorite beverage is. A bar graph would be good there because I just want to know which beverage did they like the most. Tallest bar, right? Which beverage did they like the least? Lowest bar. That's going to be very easy to see in a bar graph, right? Your line graph is focusing on changes or trends. So I have some students who will, in certain cases, say, well, I could use a line graph to see where the largest or smallest was. And you can, but that's not the goal of a line graph. The line graph isn't about just seeing where was the biggest and where was the smallest. The line graph is looking about what's happening, right, as you read from left to right on the graph. Are my lines going up? Are my lines going down, right? We're looking for those patterns of how it's changing, right? The trend that you see. So that's going to be a distinction between a bar graph and a line graph, is the emphasis. Line graphs are emphasizing changes, not just absolute what's the biggest, what's the smallest. In science class, we're going to do a slightly different version of a line graph called a scatter plot. In both a line graph and a scatter plot, you have x and y coordinates that you plot points. But in a line graph, what you would eventually do is you would connect the dots with those points. And when you connect the dots, you can end up with very jagged lines, right? Your lines can bounce up and down whenever you do a line graph. When you do a scatter plot, though, you do not connect the dots. You would have what is called a best fit line. And our computer software that helps us make graphs, they use the word trend line. A best fit line or a trend line. So what's the difference here? In a scatter plot, when you put on a trend line, the trend line doesn't even have to touch a single dot. The trend line, as the name implies, is just following the trend of the dots and how the dots are organized. Are they going in an upward direction? Are they going in a downward direction? Does it look like they're going in a straight line? Does it look like they're going in an arc? Yeah? That's what you're looking for with the trend line. So by definition, the trend line goes as close to or through as many of the points as possible without like bending and making it wavy or jagged, right? You have to keep it smooth, and it's generally a straight line. You can't make it a wavy line, or it's a nice smooth arc, right? Those are the only kinds of trend lines that we generally see. There are a few others, but those are the two main ones. We used to have to try to do these ourselves, but thankfully computers can do it for us now. So our graphing programs, Microsoft Excel, Google Sheets, all of those can handle that. All right, so I used to go through, just reminding you, with our graphing, your worksheet for homework is going to review the difference between the independent and the dependent variables. So make sure you feel good on that. But I don't believe it talks extensively about controls. So remember, the idea with controls is you want to try to keep everything as much the same as you possibly can. Like in the case of our paper towel lab, everything with our paper towels the same as much as we possibly can, except for what we're measuring, right? We have our two different brands of paper towels, and then we're measuring stuff. So, just spoiler alert, how many of you in your procedure controlled for the size of the paper towel? Or did you just say grab a sheet? Well, you don't know how big it was. Was it the little select a size? Was it the full size, right? Or even then, are they still the same? There's some that are full size, but they're not quite as big as others. That's going to affect the measurement that you take, right? Because you didn't control for the size of the paper towel. That was a big one in the paper towel lab that a lot of students will sometimes miss. But it can be various things. If I were testing fertilizer on plants, I would make sure I'm using the same kind of plant to start with, unless that's part of my experiment. But I would make sure that they're getting the same amount of light. They're getting the same amount of water. They're in rooms with the same temperature, right? I need to make sure that all of those other conditions for growing plants are the same except for the fertilizer, right? Those would be controls. Now, some students are like, but what about control groups? That's a different thing. We're just talking about variable controls. So you're trying to make sure anything else that could be different, you're not letting it be different. The only thing that should be different are the independent and dependent variables. Right? So with our paper towel lab, the independent variables are the brands of the paper towels, right? I want to know brand A versus brand B. And then my dependent, it depends on your procedure. It's whatever you measured. Yeah. All right, so with that, for number 5, I need you guys to write this out, and you're going to letter A, B, C, D, E, F, but I'm going to jump to a different screen. On that screen, there's going to be statements. And based on those statements, we are going to decide if the best graph to be used would be a circle bar or line graph. You do not need to copy down the statements. In your notes, you're simply going to write circle bar or line graph. But we're going to practice together so that we feel like we would be good on a test question doing the same thing. Okay? So here we go. Jumping screens. You don't need to copy these statements, but I'm not going to put them back on that other sheet. You guys need to write them down as I do them. So here's where we are. There's our A through F. Okay? So let's start off with letter A. If I need to make a graph and I'm trying to represent the segments of the population who plan to vote for a certain candidate. Segments of the population who plan to vote for a certain candidate. My choices are circle, bar, line. We're going to go Austin. I hear bar. I hear circle. Who wants to make an argument? Go.
Well, it's a part of a whole, because it's a segment of the population, so that's how we use it.
So first off, Austin, I definitely see there's a scenario where a bar graph could work, right? If you're just like, you just want to know who's getting the most votes. But here that phrase segments of the population being the whole, like maybe they want to know about women and men, like, hey, they're all voting for one candidate, but how many are women or men or different ethnicities or something, right? So that segment of the population is what I would zero in on to say they probably were looking for, and you guys write this in your notes next to letter A circle graph in that case. If they just said, you know, who's voting for which candidate, that one I would probably say would be a bar. We just want to know which candidate is getting the most votes, right? All right, letter B, the average monthly temperature of 2 cities. The average monthly temperature of 2 cities. What do we think, Noah?
Line.
I hear line. Do we agree? 2 cities, average. Are they trying to, do you think they're trying to say like how they're changing? Or do you think they're just saying, hey, we've got these 2 cities and I just want to know who's raining, where is it raining more? What do you think?
They're comparing, so probably bar.
Yeah, I feel like the 2 cities, right, is the comparison. There is some wiggle room sometime though. So I do want to convey that. Like there are different circumstances where depending on what I'm trying to emphasize, I would switch to a different graph. Right? The fact that it said monthly, that might have been confusing because you're thinking like, well, they're tracking every month. But I think the 2 cities, that's what they're comparing. I would say a bar graph would be more appropriate. All right, letter C, the amount of fat in 3 different kinds of potato chips. Amount of fat in 3 different kinds of potato chips. Circle, bar, line. What do we think, Emma?
Bar.
Bar. This one I think is unquestionable, right? Amount of fat. That's not tracking changes. It's just, hey, which potato chip has the most fat? Right? Bar graph comparing. That's going to be the easiest. Percent by mass of elements in the Earth's atmosphere. Percent by mass of elements in the Earth's atmosphere. Braden. And what clued you into circle? Yeah, guys, anything with percents. That's part of a whole. Right? So that's what I did in my math class. We turned our times into percents based on a 24-hour day. All right, letter E, your scores on math quizzes during a year. Scores on math quizzes during a year. What do you think, Sophia?
Line.
I hear line. What made you think line?
Because scores on especially quizzes are like a lot more often.
But what part of that statement made you pick line? There's some
During a year.
during a year.
Over time.
Changing, right? The during the year is what I zeroed in on there to say that that would be a line graph. Question.
And there's no comparison.
Yeah, and there's no comparison. Yeah, if I like said, you know, make a graph of my unit test scores, maybe that could be a bar graph because I want to see which unit I did the best on. And one might argue, but Mrs. Tate, can I also see that on a line graph? Yes, it's not that you can't get that information, but that's not the goal. Here, this during a year makes it seem like I want to see, like, are my grades bombing when I'm in season for my sport, but then they're doing better? Or on the holidays, is something messing me up, right? Like, that's what you would be implying here during the year. All right, last one. The effect of a hormone on tadpole growth. The effect of a hormone on tadpole growth. What do you think, Elle? This one's going to be line. Now, I know you may not have enough context here, but I will say, when you see these phrases, the effect of on something, right? Those are generally looking for trends. So, based on the phrasing of that statement, I would assume that they have their tadpoles, and some of them get no hormone, some of them get a little bit of hormone, some of them get a little bit more, some of them get a little bit more, so that they're actually trying to see how much of the hormone and how that affects the growth. So you can set up a nice line graph there with amount of hormone on your x-axis because you controlled that, and then the growth of the tadpole on the y-axis, right? So line graph for me for sure on that one. But again, part of it is I'm very comfortable seeing this effect of on, right? And that is almost always a line graph. Scatter plot really is what we would probably do. Okay. All right, so questions on how to pick the right kind of bar graph, or type of graph, circle, line, bar. Okay. All right, so jumping back to my notes, you guys have your answers there, right? I'm not going to fill them in now. And number 6, what's also not on your sheet, is we're just going to go over some of the basic shapes of graphs whenever you do best fit lines and what words you could use to describe those relationships. So you don't have to make these large. We're not putting a lot of detail on the graph. It's just about what the line looks like. Okay. So I'm going to go ahead now, put in my lines. And these would be trend lines or best fit lines because they are nice and straight or very smooth and curved, not jagged or wavy. All right, so I'm going to start up here in the top left. What words could I use to describe this relationship? The one you'd probably see the most is a direct relationship. A direct relationship means that as one variable increases, so does the other. That's why the line's going upwards. Another word you might also see with that is positive. Positive, though, isn't quite as informative because it doesn't tell me, or I'll say this one's also going to be positive, right? So the other word I could use to describe this relationship is linear. But if I say it's a direct relationship, direct already implies the linearity of the relationship. So direct kind of takes care of both positive and linear together, right? But if I didn't say direct, then I'd say it's a positive linear relationship. So those are the two things, either direct or positive linear relationship. So here, we would say that this is a negative linear relationship. We don't have another term for it, just negative linear. All right, moving to the top right. We're still going up, so we're still describing this as a positive relationship, but now it's not linear. What is the word we can use to describe whenever we got those arches? What do you got, Manny? Exponential. And in the context of biology, sometimes you'll hear exponential growth, right? If you have organisms involved, that's, that doesn't always fit with chemistry, though. Okay. All right, and so this last one here. This is a graph for an inverse relationship. The inverse relationship implies two things. Number one, it implies that it's negative as one variable is increasing, the other one is decreasing, but it also implies the exponential nature. So you'll notice that we have separate words for those two, direct and inverse, but we don't have separate words for the other two. Right? But guess what? These two are the most common. That's why we have those words, direct and inverse. Okay. So I do have a few more words that I'd like to define before we get to our test review next week, but we're getting towards the end of class. So I'm going to pause on this. All right, we will pick this up on Monday. But what that means is I want to make sure we're good to go for this paper right here. So this is number 16. Make sure for your binder quiz, number 16. And I only need the back of it. The front of it is just text. So you're only doing stuff on the back. You need to read the front. I saw some people who were highlighting. Awesome. Like, that's a good thing, especially helps you find your answers. But read through the front. Especially here, it talks about how you actually set your scales on graphs. Make sure you pay attention to that. All right? And then on the back, you're going to answer these questions here using the text on the front. And then I mentioned in class, guys, if you did not write this down, you're going to want to do this. Your mass of your liquid is your independent variable on your graph. That's going to determine if you should put it on the X or the Y axis. But when you make your graph, guys, I expect that you are stretching it out to fill the entire grid. Your last point, spoiler alert, better end up somewhere in this corner. Right? Not over here. You don't want your graph just to stop right here in this area. Okay, make your graph nice and big. Once you have your graph, you're going to be able to answer these questions interpreting the graph. And then lastly, it's asking the density of the liquid. We need to remember the formula for density. What is the density formula? Density equals mass divided by volume. And if we look at this data table, oh, we have mass, we have volume, right? Question.
What unit should we use for density?
You would cancel out anything that you could, otherwise you leave the units that were there. It also came up that somebody pointed out that that was milliliter. Just so you know, a milliliter is equal to a cubic centimeter in terms of volume. They both measure volume. Milliliter often used for liquids, centimeter cube typically for solids, but they sometimes will use centimeter cube for both. Right? So a milliliter is a centimeter cube. Those units are interchangeable because they represent the same volume. Right? All right, and so that's just the backside, what is due tomorrow. What else are we going to have tomorrow?
Wow.
So we're going to have
Closed-toed shoes.
closed-toed shoes, right? Have your closed-toed shoes tomorrow. Questions? Okay.